graphing the derivative function. Our objectives are to graph the derivative function and to identify where a function has no derivative. Remember that derivative means slope of a tangent line. When graphing the derivative f prime of x of a function f of x, it's a good idea to think, let's see if we can draw a tangent line, if we can, and then ask ourselves, what is the slope like? Meaning 0, positive, negative, maybe I can't draw a tangent line and therefore the derivative does not exist. Let's take a look at this function over here off to the side. This is labeled as y in the graph. We're going to call this y f of x. Down here, exactly below this coordinate plane, we are going to graph the derivative function. So we're going to call this y f prime of x. Let's begin by looking at where f of x has horizontal tangent lines. So again, we're going to think about drawing a tangent line, but it's easiest to start with these horizontal tangents. Up at the top of this local maximum, we can draw a little tangent line that is horizontal. The slope of a horizontal line is 0. So it's easy to graph that value on the derivative graph. Notice that this is at the x value, -2. So down here on my derivative graph, I am graphing the value 0 at the x value, -2. Same location, but because the derivative means the slope, I am graphing the value of the slope, and the value of that slope is 0. So I am graphing the value 0 at that location, -2. Do you see another place where there's a horizontal tangent? That's right, at this local minimum. If I draw a little tangent line, it is horizontal, and that's another place where the slope is 0. And because this is a graph of the slope values, down here at that same x value of 3/2, I'm going to graph the value 0. I am graphing the values of the slope. There is a horizontal tangent on the function. The slope, or the derivative, equals 0. Those are the only places where the slope is 0. So now we step it up and find places where there is a positive slope or a negative slope and estimate those values. About here, at this point, -4, -3 on our function f of x, I'm going to draw a tangent line. So a line that looks tangent to the function. Now I'm going to think about, what does it look like that slope is? Well, it's definitely a positive slope. If I draw a little right triangle and I think about the rise and the run from endpoint to endpoint of this little line segment, it looks like the rise is about 3 times as much as the run. So I might say that the slope of this little tangent line is approximately +3. Maybe I'm going about up 3 and over 1. These are estimates that I'm doing when I don't know exactly what the slope is. So I'm estimating this slope is about +3. So at this x value of -4, I am going to go up to about where the y value is 3, and I'm going to plot that point. Whether or not I have that slope exactly correct, I do know that because the function has a positive slope, the derivative has to be above the x-axis. Because if I'm graphing the slope and the slope is positive, this value is above the x-axis where the y values are positive. Here's another place on the graph where if I draw a little tangent line, there's a positive slope. If I do a little right triangle and I go rise over run, this time it doesn't look like this line is as steep as that line was. So I might estimate more that this is about +2 of a slope. Maybe the rise is about twice as long as the run. It's an estimation, but it definitely is a positive slope. So over here where the x value is 3, I go up to about 2 and I graph the point +2. Let's find where there is a negative slope on the function. How about here at the point 0, 0? If I draw a little tangent line, I see that that definitely has a negative slope. If I draw a little right triangle to estimate the rise over the run, it looks like it has a similar slope to this one, just where this one was positive, this one is negative. So I might say that this slope is about -2. So I find the x value 0, that's the location, and I go down to about -2. Now I may not have the exact slope correct, but what's the most important part is that if f of x has a negative slope, the derivative, the slope value, is below the x-axis. Now that I have some ideas about points on my derivative graph, I'm going to connect those points with a smooth curve. Notice I'm doing my best to connect with a smooth curve. And this is approximately the derivative function. Now, fortunately, we tried our first one from a smooth, curvy function where the derivative is always going to exist. But if f of x has corners, vertical tangents, cusps, discontinuities, places where either we cannot draw the tangent line or the tangent line does not have a slope, then f prime of x does not exist. There'll be jumps, asymptotes, or holes on the graph of f prime of x. Let's look more into that. So remember that a function is differentiable at a point if you can take its derivative at that point. Differentiable means you can take its derivative at that point. And taking a derivative means you can draw a tangent line and you can find the slope of that tangent line. So here are some examples where a function has no derivative. In other words, it is not differentiable. The first example is a corner. A corner could look like this graph. F of x equals absolute value of x. Notice that if I were to try to draw a tangent line at this sharp point, it's like a seesaw. There's really not a place that I can draw a tangent line and that line would rest. Another way to look at it is the slope of the tangent line coming from the left. That's a little negative, kind of hard to see, but this right here means the slope from the left does not equal, and this is a little plus sign, the slope from the right. These are not equal to each other. From the left, that's a negative slope. From the right, that's a positive slope. And if the slope from the left doesn't equal the slope from the right, then there is no slope at that point. A vertical tangent is another instance where the function is not differentiable. Notice that I can draw a tangent line, this line right here, that is touching at just this 1.00 on this graph of f of x equals cubed root of x, but you cannot find the slope of a vertical line. That's an undefined slope. What this is showing us right here is that the slope from the left equals infinity. These slopes are getting more positive, infinitely positive, but infinity is not a value. Technically, that's a limit that does not exist. And this is saying the slope from the right, also infinity, and does not exist. So this is showing us that these slopes from the left and right do not exist. We cannot find the slope of a vertical tangent line. A cusp is basically another place where we have a vertical tangent. It's just that the slope from the left is negative infinity and the slope from the right is positive infinity. Either way, these are still slopes that do not exist. In this graph of f of x equals x to the 2/3, I can draw a tangent line just like I could in the previous function, but it's a vertical tangent line where I cannot find the slope. Therefore, I cannot take the derivative. The function is not differentiable. Finally, a discontinuity, such as at the x value 0 on this graph of y equals h of x. The slope at a discontinuity does not exist. Why? Because the limit of this part of the slope does not exist. Another way to think of it is I can't draw a tangent line. And if we can't even draw a tangent line to begin with at a point, we can't find the slope. So at a discontinuity, there is no derivative. The function is not differentiable. Now, it's important to note that if a function is differentiable, then it will have to be continuous. Another way to say that is differentiability implies continuity, but continuity does not imply differentiability. Here are 3 examples that we just looked at. This is a continuous function, this is a continuous function, and this is a continuous function. But none of these 3 functions are differentiable at a certain point. So you might have a continuous function, but it's not differentiable. Now, if the function is differentiable, then it will have to be continuous. We'll keep that in mind as we work. In these examples, let's use the graph of f of x, shown below, to graph f prime of x in the same coordinate plane. So again, when we are graphing the derivative, we want to think about the slope of the tangent line. This is a linear function. Let's label this graph f of x, or f for short. Now, there are no numbers on my coordinate plane, so I don't know exactly what this slope is, but I do know that the slope is a negative value. So I do know that when I graph f prime of x, I have to graph it below the x-axis. Now, because this is linear, it always has the same slope, so the derivative will always have the same negative value. This is my graph of f prime. In this absolute value graph, let's label the original graph f. The first half of it, this left side, is very much like this, where it has a negative slope and the same negative slope because it's linear. So I'm going to graph the derivative like that. Now, this is a corner right here, so there is no derivative at that point. Therefore, I will put a hole. I'm graphing f prime, and if there's no derivative, I can't put a point on the f prime graph. Now, this other half has a positive slope. So I'm going to graph a positive derivative, and because it's symmetrical, however far below the x-axis I put this first half of the derivative graph, I'm going to go approximately the same distance above the x-axis to graph the rest of it. So I've got the negative values and the positive values for the negative slope and the positive slope. This graph, again, we'll label it F, and let's check out what the slope should look like. Now notice if I think about the tangent line, it starts with a slope that is positive, and as we move to the right, it gets more positive and more positive. In fact, it's getting infinitely more positive. This is a cusp. We can draw a tangent line here, but it's a vertical tangent line. So think about what we just talked through. The slope values are low, but positive, and then they get higher and higher and higher, and then infinitely, infinitely high. Asymptotic behavior there where there is a vertical tangent. So my graph of f prime will have a vertical tangent, a vertical asymptote at that vertical tangent. Now what happens on the other side? If I think about drawing a tangent line that has a negative slope and a very, very, very steep negative slope. So I start my derivative values very low, and this is always a decreasing function, always a negative slope, but getting closer to zero. So my derivative function is going to look something like this. Very negative and getting less negative and getting closer and closer to zero. And number 4. Let's label this original graph F and think about the slope of this first piece. That has a slope of 0, so I'm going to graph my derivative at 0. Now I have a discontinuity, so the derivative can't exist. Then I have a very steep negative slope, very much like this one, and therefore a vertical asymptote for the behavior saying it's starting infinitely small, and it always has a negative slope. The function always has a negative slope. It gets closer to a slope of 0. So this is going to be coming up towards 0. And there's my graph of f prime. It'll get easier with some practice. Thanks for watching.